all of us know how to determine the volume of a parallelepiped in Rn. So suppose V1, V2 dot Vn are n vectors in Rn, then we define the parallelepiped spanned by V1 to Vn to be just this set T1 V1 plus T2 V2 plus dot Tn Vn, where T1 to Tn come from 0 to 1. Okay, so this is defined to be the parallelepiped spanned by the vectors V1 to Vn. Now we know that the volume, that is the signed volume of this parallelepiped, is nothing but determinant of V1 dot Vn. You put these V1 to Vn as column vectors, shove them together into an n cross n matrix and take the determinant. That's going to give you the signed volume. Now our ultimate goal is to define integration on manifolds. The question arises, what is it that you want to integrate on a manifold? The correct thing, the correct object that can be integrated on a manifold is a differential form. So suppose you have a D manifold, a D form on that manifold is nothing but a alternating multilinear function defined on the tangent space of that manifold. Just like the determinant is an alternating multilinear functional defined on Rn, the general differential forms are alternating multilinear functionals defined on the tangent spaces. To each tangent space, you might get a possibly different alternating multilinear function. So we have to define the notion of smoothness of such forms, continuity, and so on and so forth. So we have a lot of work to do. So the first few definitions I would prefer to give for a general vector space. There's nothing special about Rn. Doing it in Rn is not going to confer any additional simplicity. So I'm going to make the first few definitions in the general context of a vector space. So definition. This is the definition of alternating K form on a vector space. So the definition is as follows. Let V be a finite dimensional real vector space. So throughout, V will always be a finite dimensional real vector space. So in the future definitions and theorems, I might sometimes forget to include this as a hypothesis. Alternating K form on V is a function omega from V times dot V, this is K times, to R, that satisfies number one, multilinearity. What multilinearity says is, if V1 to Vn is an element of not V1 to Vn, V1 to Vk is an element of Vk, then omega of dot comma V2 to Vk comma omega of V1 comma dot V2 to Vk dot omega of V1 to Vk minus 1 comma dot are all linear. This is just elaborately saying that a K form is multilinear, or rather linear, in each one of the slots. 2. The second condition, this is the important one, and this is also motivated by the determinant. Omega is alternating. Omega is alternating. What this means is, if sigma is a permutation of 1 to k, is a permutation of the first k natural numbers, is a permutation, then omega of v1 to vk is the same as the sine of sigma into omega of v sigma 1 comma dot 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 v sigma k. So what this is saying is, if you shuffle around the entries, the slots, then you get a sign plus or minus 1, and that plus or minus sign is exactly coming from the sign of the permutation that does this shuffle. Okay, so this is the definition of a K form. Now, for convenience, let me also introduce one more notation. Just this first condition. So if only the first condition is satisfied, that is multilinearity, if only the first condition is satisfied, we say omega is a K tensor. Okay, this will be useful terminology. And writing alternating K form is a little bit too much, so we will just abbreviate alternating K form to K form. Okay, it's understood that alternating K form and K form are the same. Okay, so we will just drop the adjective alternating whenever possible. Okay, so I'm going to assume that you have proved the following in linear algebra. This is the first example also of a differential form theorem. So this fact I will not prove in this course, but it comes as a corollary of one of the results. The determinant det from Rn times dot 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 Rn. I am treating each Rn as a column vector in the matrix on which the determinant is defined. So I can treat the determinant as a function defined on Rn cross Rn cross Rn n times to R is the unique n form on Rn cross dot 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 Rn with the additional normalization condition that determinant of E1 to En is 1. Okay, furthermore, if V1 to Vn are in Rn, then determinant of V1 to Vn gives the signed volume of the parallelepiped spanned by V1 dot 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 Vn. Okay, now I'm going to give you several examples of differential K forms, and all of them are going to come from this determinant function. So what is this example? Well, recall that on Rn, dx1 to dxn are the dual basis vectors. Essentially, dxi is just ei star. So the example I am about to give is the following. Let I equal to I1. It's a tuple actually, not a set I1, I2, ik be a k tuple of natural numbers with 1 less than or equal to I1 less than or equal to I2 less than or equal to ik is less than or equal to n. Okay, choose some this is ik, not in. Choose k integers from 1 to n and put them in this increasing order or non-decreasing order. Note, I am not assuming that I, j and I, r are going to be different always. Many of them could be the same. Now we are going to define the k form dxi. So this I is coming from this I. We define the k form dxi on Rn as v1 to vk maps to the determinant of dxir of vs. Okay, where r comma s run from 1 to k. Okay, so what we are going to do is we are going to pick these v1 to vk, then we are going to compute this matrix dxir vs, whose rth entry is just nothing but the evaluation of the irth dual basis vector evaluated on vs. Put this together as a matrix and then take the determinant. Now why is this a k form? Well, that this is a k form is immediate from the properties of the determinant. Okay, so and this is left as an exercise for you. Exercise, show that dxi is indeed a k form. Okay, now what we are going to do is let's analyze this example a little bit more. If I1 ik are not distinct, note I said that I am not making the assumption that they are distinct, then two rows of the matrix will be the same. So dxi is just 0. So dxi is just identically 0 in this case. It's a 0 form. Okay, not as in it's a 0 form as in it's a function. What I mean to say is it's an identically constant 0 on all vectors v1 to vk. Okay, now let's denote the standard basis again by no, what we do is if e1 to let me just change the notation a bit. Let ej1 comma ejk be a k tuple of standard basis vectors. So what I'm doing is I'm taking the standard basis vectors and taking some k of them and putting this inside this k tuple. Again, I do not assume that this tuple has no repetitions or any such thing. It could all be E1, for instance. I'm making no such assumption. Okay. Now, what happens when you analyze this differential form acting on when you see dxi of ej1 ejk, note that dxi of EJS, if you look at this, if you look at dxi of EJS, this is 0 unless I is JS, okay, and 1 if I is equal to JS, okay. So what this means, if the tuple had a repetition, then the matrix will have two columns the same, okay. That means dxi will be 0 on all pairs, all k tuples of basis vectors with repetition. Okay. Now let's take another situation where it's going to be 0. Suppose for some JS is not equal to I1 ... ik. So you have an index, you have a basis vector with an index that is not the same as any of the indices that appear in dxi, the definition of the form dxi. In this situation, observe that one column in the matrix will be 0. That one column in the matrix will be 0. Okay. So net upshot is dxi will be non-zero only if there are no repetitions in I, in I, and the k tuple of standard basis vectors is some E I pi 1 comma ... E I pi k, where pi is a permutation of 1 to k. That is, the k tuple of standard basis vectors that you take and apply dxi to should also be ei1, ei2 ... eik, but you could mix them around, shuffle them around by a permutation pi. And it is also obvious, it is also clear. So whenever I say it is also clear, it is also obvious, that means it's an invitation for you to work out the details. It's also clear that dxi of this ei pi 1 comma ... ei pi k is nothing but sine of pi, the sign of the permutation pi. Okay, so this was an elaborately worked out example of K forms on Rn. We had defined it using the standard basis vectors E1 to En's dual dx1 to dxn. These forms will play crucial roles in what is about to come. Okay, now notation K forms will be denoted alt k of v. As an exercise, show that alt kv is a vector space. Okay, now I'm going to end this video with a characterization of K forms, especially the alternating condition. Okay, so this, let me call it a proposition. So let omega from v dot 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 v k times to r be a tensor, k tensor. Then the following are all equivalent. Number 1, omega is alternating. Number 2, omega of v1 to vk is 0 if sum vi equal to vj. Number 3, of course I is not equal to j. Number 3, omega of v1 to vk is 0 if the list of vectors v1 to vk are linearly dependent. Finally, if two slots are interchanged, then omega changes by a sign. Okay, that is, if you want to make this more precise, tau from 1 to k to 1 to k is a transposition. That means just one pair I comma j are interchanged. Then omega of v1 to vk is equal to omega of v tau 1 comma dot 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 v tau k, and a negative sign. Okay, transposition introduces one negative sign. Let's prove this. This will give several ways of characterizing K forms. You can check, these properties will be repeatedly used in the rest of the development. So of course, sign of a transposition is -1. So from this fact 1 implies 2, because if you have two vectors in v1 to vk to be the same, just consider the transposition that interchanges these two vectors, then you should get back the same value. But the fact that one says omega is alternating will introduce a negative sign. This will be possible only if omega of v1 to vk is 0. Okay, so suppose 2 is satisfied. So let's recall, 2 says that omega of v1 to vk is 0 if sum vi equal to vj, I not equal to j. Okay, now let v1 to vk be linearly dependent. Without loss of generality, assume that vk is some linear combination of the preceding vectors plus ck minus 1 vk minus 1. I'm just assuming that it's the last vector that is going to be the linear dependence comes from the last vector. There is really no loss of generality in this, and I want you to check why. Now when you apply omega to v1 to vk, just by the fact that it's multilinear, which is the global hypothesis on omega, you get c1 omega v1 dot dot dot, but the last entry is again v1. So this is v1 v2 vk minus 1 v1 plus c2 omega v1 v2 dot vk minus 1 v2 plus dot ck minus 1 v1 dot vk minus 1 comma vk minus 1. I'm just using the multilinearity in each of the slots. Okay, each term is 0 by hypothesis. Okay, so hence 3 is shown. All of these are just elementary arguments. So for 3 implies 4, let tau interchange v 1 and 2. Then the hypothesis 3 says that if v1 to vk are linearly dependent, then omega v1 to vk is 0. So what we are going to do is then 0 is equal to omega of v1 plus v2 comma v1 plus v2 comma v3 comma dot vn. Okay, so this just follows from 3. In fact, I'm just using the special case 2. 2 is actually a special case of 3. So I'm just using the special case of 3. I'm repeating the same vectors v1 plus v2 in both the slots. But by multilinearity again, this is just omega of v1 v2 dot vk plus omega of v2 v1 dot vk. Okay, the other terms will have repetitions and therefore will vanish again by the hypothesis. So this is 0. So that means omega of v1 v2 dot vk is equal to omega of v2 v1 dot vk with a negative sign in front. Okay, so this essentially proves 3 implies 4. I've just interchanged the first and second, but it's very clear that it will hold for any transposition. This essentially proves 3 implies 4. Finally, 4 implies 1 is just the fact that any permutation is a product. Permutation is a product of transpositions. In fact, another fact that is needed is the fact that the sign of a permutation is nothing but the product of the signs. When you write a permutation as a product of other permutations, then the sign of the permutation is the product of the signs. That is also used. It's a product of transpositions. Okay, so this concludes this proof. It's just elementary linear algebra and elementary properties of permutations. So we will continue our study of differential forms in the next video. This is a course on real analysis and you have just watched the video on differential forms.